Now, what drives the current? Well, you know the answer to that. It's the battery. Without the battery, you're not going to get any flow. We call that the electromotive force. Years ago, at my birthday, some friends gave me an old textbook. It was a physics book written by a very prominent physicist. And it was a book that was intended for physics teachers on how to teach physics. And I just love the chapter on electromotive force. It starts out, tell your students quickly the name and hope they forget. Because that name is misleading. This is not a force pushing charges around the circuit. It is not in any way a force. It's just historically we've called it that, and I wish we had not. What it is, the battery acts like an energy pump, driving current around the circuit. The EMF is how much energy the battery gives to each coulomb that goes through the battery. Any coulomb that goes from the negative terminal to the positive terminal is chemically handed, if this is a 12-volt battery, it's chemically handed 12 joules of energy. Now, I don't want you to misunderstand what that means, okay? It's not kinetic energy, okay? In other words, when the charges come into the battery, they're not all, oh, I'm so tired. And then they come out the other side, like they just had an energy drink. No, it's like a boulder at the bottom of a cliff. You look at it, it's just sitting there. You move it to the top of the cliff, you look at it, it's just sitting there. You take a picture of it at the bottom, you take a picture at the top, it doesn't look different. But the boulder at the top of the cliff doesn't want to stay there. It wants to get to the bottom of the cliff. And that's what the battery does. It takes a coulomb, like a boulder, and puts it where it doesn't want to be. And then that coulomb tries to get back where it wants to be, back to the negative terminal of the battery, back to the bottom of the cliff. And in doing so, it goes through the bulb. Okay? It's just like gravitational energy, but it's electric potential energy. Electric potential. The kind we were talking about at the exam last Tuesday. Okay? Now, this is measured in joules per coulomb or volts. And it's just the battery voltage. Now, for historical reasons, because we've typically called the battery an electromotive force, we often label a battery with this symbol epsilon. But it really should just be a delta V. A delta V. Okay? Now, if I measure the voltage across that battery from A to B, what I find is the voltage is 12 volts or 12 joules for each coulomb. And that's this idea of taking that coulomb and putting it at the top of the cliff. If I measure the voltage across the bulb from C to D, what I find is that I get minus 12 joules for each coulomb, or minus 12 volts. And what I interpret that as is that I give each coulomb 12 joules of potential energy here, and it loses that energy in the bulb. It doesn't lose it in the wire because it's easy to go through a wire. There's no vert required to go through a wire. But the filament of a bulb is hard to get through. That's high resistance. And so it has to do vert to get through that filament. And that's where we change that energy, that's electric potential energy, into heat. And then if it gets hot enough, it starts to glow. If it gets hot enough, it glows red. If it gets hotter, it glows white. And that's what causes the bulb to help you find your tent. Okay? This is the cartoon that I want you to carry around with you. Each of those balls represents a coulomb of charge. And the darker red the ball, the higher the electric potential energy it has. And it just goes around. You can think of those coulombs as dump trucks. They go through the battery, and as they do so, they pick up 12 joules of energy. They take that 12 joules of electric potential energy, and they deliver it to the bulb. And then those dump trucks go back for more. Now, here's the thing. It's the energy that is carried to the bulb and used up, not the coulombs, not the current. If I were to put ammeters here and here, they would read exactly the same thing, because I've got the same number of dump trucks going past every second. It's just that these dump trucks are at a low energy, these dump trucks are at a high energy. But the number of dump trucks per second, that's the current that we measure. I call that the what goes around comes around principle, which typically is associated with gossip. In a small town, eventually you'll hear it. Okay? See if your neighbor's on the bus so far. Let's not lose anybody. Okay. We've talked about current, and we measure current with an ammeter, measuring amps. We measure voltage, and by that I mean voltage difference, with a voltmeter, which looks a whole lot like an ammeter. And we're going to find it has very, very similar guts inside. But there's one very important difference between a voltmeter and an ammeter. When I connect it, I don't connect it in series like I did the ammeter. What I'm looking for is a voltage difference from A to B. And since this ammeter has two leads, danger, danger, Will Robinson. You're too young. Okay, if I want the voltage difference from A to B, I touch one of these leads at A and one of them at B. So I come in here and I touch it on one side of the bulb and the other side of the bulb. Now, since I've got wire connected to those sides of the bulb, I could also just hook it in there and there. Now watch the bulb while I connect that. Did the bulb get dimmer? No. No, it did not. It also didn't go off while I was connecting it. When I'm connecting an ammeter, I got to disconnect it. I got to break the line and shove it in so that all the current flows through the ammeter. But the voltmeter just takes a trickle of the current, a trickle of charge. In other words, I'm hooking it up in parallel to that bulb, and I want most of the current to go through the bulb. I don't want to change the brightness of the bulb, so I just take a trickle of the current out, and I measure for that trickle of current how much the potential energy changes. And that's how I get the voltage. Now, think about this. If all the current has to go through this guy, and that doesn't change the brightness of the bulb, we said that this guy must be really, really easy to get through. This guy's hooked up in parallel. The current, if you look at it, either has to go through the bulb or through the device, through the voltmeter. Not both. It has to choose this or that. And we want nearly all of it to choose this one. So is this going to be easy to get through or hard to get through? Hard to get through. This has a huge, huge resistance. And that is a principal difference between a voltmeter and an ammeter.